Hello everyone, welcome back to Microeconomics. So like I said last time, this week we will spend some time to equip you with some mathematical tools for microeconomics. So we start with maximization of a function for one variable, and then we move up to the cases where we have several variables in a function, and we repeat the concept of elasticity and how to derive them. The next thing will be the constraint maximization. And at the end, we look at the concave and homogeneous functions. Those are important functions in microeconomics, which we will also see quite a lot in this course. So let's go. First thing, maximization of a function of one variable. Suppose we have a profit function pi, which depends only on the quantity sold of the good, denoted Q here. Now let's take a moment to look at this graph. So if we move from Q1 to Q2, what happens to the profit? It will also increase, right? It increased from pi 1 to pi 2. So profit and quantity in this case moved in the same direction. Increased quantity, increased profit. One way to express this relationship is to write the change of profit over the change of quantity positive or larger than 0. We can also simply write delta pi for the change in pi over delta q for the change in q positive or larger than 0. So the limit of this ratio for small changes, very small changes in q is called the derivative of the function pi. And this can be denoted as df or d pi over the q, or just simply f prime q. So what is the derivative of a function at a certain point? About notation, if we go back to the point where quantity is q1, we denote the derivative at this point as d pi over the q, and then vertical bar at q equal to q1. We read that evaluated at q equal to q1. Now let's think a bit about how we can increase the profit at certain level of quantity. Go back to the point where we are at Q1. Now, if we want to increase profit, we saw before, we have to increase the quantity, right? So at this point, the derivative of profit with respect to quantity evaluated at Q1 is larger than 0. On the other hand, if we are at Q3, we can increase profit by going further, because at this point, profit decreases. So we actually have to go to the left, which means we reduce the quantity sold, and only then profit increase. Because of that, we see that profit and quantity moves in opposite direction, and the derivative of profit with respect to Q at this point is negative. However, if we are at Q start, here is the maximum profit point at pi start according to the graph. We would not get better off by moving either to the left or to the right, and a very small change of Q at this point will cause a 0 change in profit. Remember, very, very small changes and we also don't want to move from that point because it's maximum, right? So at that point, the derivative of pi with respect to q equal to 0. So the derivative is the slope of the function. Then what is the slope? The slope, by definition, shows how the value of the function change when the variable within that function changes. Okay? Having said that, we come to the first and second order first and second order conditions for the maximum, which is the derivative of the function, here the profit function pi, with respect to q must be equal to 0 at the maximum point. However, that is not the only thing we have to take care. Why? Because there will be a case where we have a function like this. Here's q. And at this point, the profit is minimum, but still the first derivative is 0, because here also very small change will result in a 0 change in profit. And you will see in further lectures later. Therefore, in order to avoid this situation where we end up in a minimum point, but we thought that was a maximum point, we need a second derivative. That is also the second order condition. It says that the second derivative of pi with respect to q evaluated at q star at the maximum point or the optimum point must be smaller than 0. So intuitively, you would think that if we change from this point either to the left or to the right, we stepped down or we decreased the profit. That's why it's smaller than 0 here. But we could talk about it more in the next slide. So the second derivative can be denoted as d square pi over dq square. I'll just simply add double prime q. And the second derivative show us information about the curvature of the function, which means if it's concave or convex to the origin. We will see what means concave later. So just an example here to show why the second derivative matter for the maximum or minimum. So here we have an example of the function y equal to x to the power 3 minus 5x squared and plus 100. We will not derive the derivative here yet, but just to look at the graphical illustration now. So here the local maximum or the optimum could be in 2 points. Either this point or this point. And at those 2 points, the first derivatives equal to 0. So now the question is, how can we distinguish them between a minimum and a maximum point? So if you look at the third graph here, which shows the second derivative, you see that it's actually until here, corresponding to this point. The second derivative is negative, which just tells us what we saw on the slide before. And what does that mean? That means the first derivative is decreasing. So if that's a maximum point, it must be the case that you cannot gain any extra profit by increasing or decreasing the quantity. You will always get a lower profit. And because of that, first derivative must be decreasing. And remember, we talk about a slope. It shows how a function change when variable change. So in this case, the slope of the first derivative is the second derivative. That's why the second derivative must be negative.